All right, so let's talk about some simple graphs. About the simplest graphs that we can come up with are, terms of equations anyways, are the planes that are parallel to the coordinate planes. And these are all obtained just by setting one of the variables equal to a constant. So for example, let's sketch the graph of x equal to 2. So this is all of the points where x is equal to 2. Y and z can be whatever they want, and it turns out that this is going to be a plane, and it's going to be parallel to the yz plane. So to sketch this out, I've sort of drawn my xyz axes sort of dotted, because as you see from these pictures over here, I tried to suggest that a line or an axis is going behind a plane by drawing it dotted. So let's see, x equal to 2, let's say that's right about here. I'm going to put a dot right here at x equal to 2, just because when I draw a plane, I often like to just draw a point there just sort of for a point of reference. And now this plane should be parallel to the zy plane, which we have seen is sort of like a rectangle that extends forever, spanned by these two lines right over here. So I'm going to try to draw something that's sort of with sides parallel to that. All right, and let's draw it up to about there. Great. So now I'm going to suggest where these lines are in front of and in back of this plane. The y and z axes, the parts of them that extend beyond the plane, at least the portion of the plane that I've drawn, are this piece right over here for the y-axis and this piece over here for the z-axis. The other two parts are, in truth, both axes are completely behind the plane because the plane extends forever, but with just the portion that I've drawn, these pieces are behind the plane, and the parts that aren't aren't within the boundary of the plane drawing here are not behind it, so we can see them. For the x-axis, however, at this point right here too, that's where the x-axis stops being behind the plane and pokes out from in front of it. So from the origin to 2, we should keep it dotted, but beyond 2, we put sort of a solid line to suggest that this x-axis is poking through right there. So this is supposed to show that this plane is in front of the origin. The x-axis actually goes through it, but the z and the y-axis stay behind it for the whole time. Over here, I've drawn y equal to 4, which is parallel to the xz plane. It's this sort of vertical plane right here. This is also a vertical plane. And then z equal to 3 gives us a horizontal plane that's parallel to the xy plane, looks like this. Great. So if we can sketch some simple graphs if we restrict ourselves, some graphs of simple curves, if we restrict ourselves to working in a single plane. So for example, over here, I say let's sketch the graph of x squared plus y squared equal to 1, where z is equal to 0. So that means that we're sitting in the xy plane. That has z equal to 0. So then I'm just sketching x squared plus y squared equal to 1 in the xy plane, which is just a circle centered at the origin of radius 1. Well, here it is. This is supposed to be sitting on the xy plane. What if I did something instead and said, let's have z equal to 2, but x squared plus y squared equal to 1? Well, that doesn't change any conditions on what x and y can be, at least in terms of lying on this circle. All it changes is that the z coordinate has to be 2 instead of 0. So every point down here just gets shoved up 2 in the z direction and has a point up here. And so now we have, you know what, it looks like I meant to say z equal to 3. We push them up 3 units in the z direction, and we just get a circle up here. This circle is sitting in the z equal to 3 plane up here, but it's just the same as the circle down here, just translated 3 units up. Now what happens if we just look at x squared plus y squared equal to 1? Now I'm not putting any conditions on z. Well, that would mean that this circle is part of the graph of whatever this is, and so is this circle. Indeed, for any value of z I put down, I get a circle in the plane z equal to whatever that value is. So for example, if I let z be equal to 2, I get a circle in the plane z equal to 2. The circle is x squared plus y squared equal to 1, but with z equal to 2. And I just get a bunch of circles that lie on top of each other. And when I fill them all in for all values of z, what I end up getting is really a cylinder like this. So when I take this circle and extend it up and down, I just carve out space up and down with the circle, just moving it straight up and straight down, I get a cylinder. So x squared plus y squared equaled 1 forms a cylinder. Z can be anything, but x squared plus y squared are forced to be on this unit circle. So I get the cylinder of radius 1. Now we're going to talk about vectors. So for our purposes, a vector is defined to be a quantity that has magnitude, magnitude being a real number that is greater than or equal to 0, and direction. And by direction, I mean, for example, in two-dimensional space, you can just specify an angle that something makes with, say, the x-axis or the origin or something like that. And in three-dimensional space, you would need two angles, but that's an example of that is, say, latitude and longitude is a way of specifying, say, a direction from the center of the Earth. All right, so a very common example of a vector is something called a displacement vector. Now, if an object moves from point A to point B in space, the quote-unquote directed line segment from A to B is called a displacement vector. A is the initial point, B is the terminal point, and the vector is this arrow drawn from A to B. When I say directed, what I mean is that it matters that I'm starting at A and ending at B. If I were to look at the vector starting at B and ending at A, swapping the initial and terminal points, I would not be left with the same vector. It would have the same magnitude. This distance from A to B will be its magnitude, but its direction will be opposite. So not the same vector. Also notice that I decided to give this vector a name. I decided to name it V. When we write down a vector, we usually write this sort of half arrow on top of it. That just tells us that we're looking at a vector. So if I ever write down, say, W with this symbol over it, you understand that, okay, W is a vector. Now note, we treat two vectors as equal if they have the same magnitude and direction, even if their initial and terminal points differ. So I've drawn another picture of the exact same vector V right over here. Its initial point is C, its terminal point is D, so it's not being represented in the same exact fashion as it is up here, but it's supposed to have the same magnitude, it has the same direction, it's the same vector. So a vector doesn't care about where you start, where exactly you start or end. Also, in the context of thinking about this as a displacement vector, an object moving from point A to point B, I'm not saying that the object took this straight line path from A to B. It may have meandered its way from A to B. But again, a vector doesn't care about the path you're taking from one point to the other. It doesn't care about how long it took you. All it cares about is the magnitude, how far you've gone, and the direction, which way you went. All right. Now there's one very important vector for us to point out. That's the zero vector. You can write it as 0 with the vector notation above it. And it's the vector whose initial and terminal points are the same. And so, for example, if you just imagine a displacement vector, you start at A and you make a round trip back to A. What is the vector that represents your net change? Well, it's the zero vector. You haven't gone anywhere. So it has zero magnitude. You're not going anywhere. And it has undefined direction because, well, there's just no way to define it.